My name is Omair Majid. I am a senior software engineer at Red Hat. I work on the OpenJDK team where we work on OpenJDK itself as well as related tooling. Some of the things at OpenJDK team that we work on are performance improvements. We port OpenJDK to a lot of different architectures. Some of my colleagues ported it to a non-assembler based version. Some people are porting it to ARM64 servers. One of my colleagues sitting here is adding a new garbage collector to OpenJDK with ultra low pause times. So if you're interested in garbage collection work, definitely go to our talk tomorrow. I mostly work on serviceability tools, and that's what this talk today is going to cover. So the agenda is pretty straightforward. I'm going to be talking about a few factors that affect performance and what sort of metrics you might be interested in when it comes to getting those performance numbers. Then I'm going to talk about Thermostat and how it fulfills that role by obtaining all those things that we said we're interested in. I'm going to try and do lots and lots of demos. Some of them may not work, but we'll have fun and see what happens. Finally, I'm going to talk about plugins and how they make it possible for you to add features to Thermostat that may not be built in. And we'll talk more about that. Finally, I'll talk a little bit about getting involved. So this is an open source project. You can contribute patches, ideas, features, bugs, what have you. So let's get started. First thing, as a Java developer, once we have our application working, it fulfills its basic purpose. What do we care about? Secondary concerns. We care about performance. We care about the resource it's using. We care about, is it doing everything that it's supposed to? Does it work in the right way? If we wrote a multi-threaded application, is it using threading correctly? There are lots of questions, and we want answers. We care about lots of information that's specific to the machine that we're running on. So we may care about what OS is using. Is it up to date? Does it have the right libraries? What the CPU on the machine is like. Is it a slow, fast machine? How do we expect its performance to be? We may also care about memory. So does it have a small amount of memory? Are we talking about a few gigabytes? Or are we talking about huge amounts of RAM that may affect its performance? Christine will have a lot more to say about memory and garbage collection tomorrow. We may also care about non-uniform memory architectures where access to a particular area of memory might be faster than others. And finally, we also care about we care about input and output. So if you have a hard drive, you're doing network access, all that latency adds up. And we want to know more about what's going on there. We also care a lot about what's happening inside the JVM. So not just how much the CPU process that's available, but how much is being used by the JVM. So for example, can we run multiple JVMs on a single machine or not? We care not only about the total memory available to a JVM, we also care about the memory region sizes that are used. So do we want a small region of memory where we allocate new objects? Do we want a large area of memory where we allocate new objects? What do we do with long-lived objects? How much memory sizes do we allocate for them? And of course, what garbage collector is running? Do we care more about latency? Do we care more about throughput? Do we care about pause times? Are we willing to accept performance sacrifices to get lower pause times? And if you have a large application, some sort of middleware-based application, maybe using OSGI or something, we can have tons and tons of classes that are being loaded. So you care about what classes are loaded, what the sizes of those loaded classes are. If we're using some sort of JAMX mechanism that a lot of applications are, we may care about notifications that are being emitted. So everything that gets emitted, we want to maybe record that for future purposes. Java obviously isn't fast because it's pre-compiled. It's fast because there is a just-in-time compiler that's actually running. So we want to find out exactly what that is doing. How long has it been running? How many classes it has compiled? How many things it couldn't compile? And how long, what the sizes of those compiled things are. We also care about the I/O that the JVM is doing. So not only just how much data it's reading, how is it reading them? How many system calls is it doing? Is it using one system call to read 1 byte, or is it reading 1 megabyte in each system call? We also care about the threads. So the JVM obviously supports multi-threaded applications, and we can run hundreds of threads. But we want to know, what are those threads doing? Are they actually making progress? Are they blocked on waiting for each other? What's going on there? And then, because the JVM is such a flexible runtime, we can't just ask it for information. We can tell it what to do. So we can do things like, we can trigger heap dumps at runtime. We can invoke the garbage collector, force it to do what it wasn't doing before. We can do things like force deadlock detection to automatically find out if our threads are deadlocked and tell us exactly what's going on. But more than that, the JVM supports awesome ideas like injecting custom code. So if you have a piece of JVM that's running code, you can inject extra code in it and make it do what it wasn't doing before. So you can do things like, hey, if method A is called, don't do what A was supposed to do. Do this new thing instead. Or you can say things like, if method A expects an argument of 10 and we got 100 in an exceptional case, handle that very, very differently. So there's a lot of things you can do in the JVM. The question is, how do you do this? They're all different. There are multiple tools available, and they all work differently. In fact, there's way too many things that we want to know about. There's way too many places to obtain them from, and there's way too many things we want to do. So wouldn't it be great if there was a single thing that could help us do all that? Well, yes, that's where Thermostat comes in. So Thermostat is a serviceability and monitoring tool for OpenJDK. I want to focus a bit more on the serviceability part, not so much as on the monitoring part itself. If you are looking for a dedicated monitoring tool, this may not be the right thing. This is more of a let's monitor and then do stuff. So it is meant for OpenJDK. We develop it alongside OpenJDK. We test it against OpenJDK, and it works absolutely fine there. In Thermostat, we care about two things a lot, and those are what we call horizontal integration and vertical integration. So by horizontal integration, we mean that we want to get information from multiple hosts, multiple machines, multiple containers, what have you, collect it all in one place. So then we can study it, analyze it, and figure out what to do. We also care about vertical integration, which means across the stack. So on your machine, you may have your physical hardware, you may have your operating system on top, your runtimes, your Java virtual machine, any middleware, and then finally your application. Wouldn't it be great if we could study each of those and figure out what each part is doing, and if it's working, is it working well? Obviously, we can't do everything, so Thermostat has a plugin architecture where you can add features that aren't supported. And I'm going to do a demo later on. It's showing exactly how you can add a plugin that measures something that is specific to your application. Of course, some of us are really, low-level command line hackers, so we have a command line interface as well as a GUI, so users can point and click and do what they want, or you can just script stuff and use it like you use command line tools. Thermostat is open source. Obviously, Red Hat doesn't really need saying. We wouldn't work on something closed source. But what I want to point out here is that this is open source under the same license as OpenJDK. So if you feel comfortable using OpenJDK and contributing to it, you're okay to use Thermostat and contribute to it too. So let's actually talk about how to use Thermostat. As I mentioned, it can work in multiple ways, or it can work on a single machine, multiple machines. So there's a couple of different configurations. The two basic ways are using Thermostat Local, which runs Thermostat for your single local developer machine with a GUI. And I'm going to show that in a little bit. The other way to run it is for the shell. In that case, we do two things. We start our data collection mechanisms and then run the Thermostat shell. And this is what the GUI will look like. But you know what? Enough of me showing pictures. Let's get into demos. So let me actually fire up Thermostat. So I'm going to do Thermostat local. I have it checked out in a custom directory, so just ignore that bit. This is the latest version, so built from source sometime last week. So you can see it's doing a bunch of things. It's starting some data collection mechanism. It's starting to collect some data, and then shortly we're going to see the GUI pop up. So here you go. This is what Thermostat looks like. On the left side here, you can see that it shows all the JVMs and the machines that it detects. So my machine is named Trots. And you can see it has found a bunch of JVMs here that are running. On the right side here, you can see general information about things. So if I go into specific things, it will show more specific pieces of information. If I click on the host here, I can see some overview information. So what the hardware is like, what the network is like, what OS it is running, and the basic CPU and memory metrics. We can kind of drill down into the details here too. So you can see what the processor here is. In this case, I have 4 processors, and I can show the data for just the last minute. So this is what Thermostat is collecting, recording, and then displaying for us, and we can go back and forth in time as well. We can switch over to the memory tab here, which is showing what the memory usage on my machine looks like. So this is recording everything that the Linux kernel is telling us, such as total memory, free memory, allocated, used, swap, and buffers. And you can narrow it down by time and selection. So I can just say, show me total memory for the last minute. And yeah, that's not changing, which is great. Don't want my total memory changing at runtime. And that's the size of my used free memory. And you can play around with this. On the NUMA tab here, I can see the NUMA allocation rates. In this case, I have just 1 node, so this is really just telling me what my total allocation rate is. But if this was a multi-node NUMA machine, you'd find out what the allocation rate across multiple nodes are, and whether there are hits and misses, and whether there's something you need to look at. This last tab here is just for fun, really. It's for adding notes, so I can say this is a very important machine. Don't shut it down. And it will stay for the next developer who runs this and maybe comes back to this and says, oh yeah, this is important. So if I switch over to the GUI, to the individual JVM, I'll see a lot of information about the JVM too. So we show things like process ID, when the JVM started, who's running it, what the main class is, what the arguments are, what the JVM version is, all the VM arguments, basically anything you want to know about the VM itself. But not only that, we show CPU information. So if you're interested in finding out exactly how much CPU this specific JVM is using, you can see that. And again, you can go back and forth in time and see historical data. We also have a couple of profilers. So this one is a really simple method-based profiler. When you run it against your code, it's going to find out how long, on average, your methods are taking. I'm going to show an example of this running in a bit too. So we'll come back here. The GC tab, which might be very interesting to some of us, is showing garbage collection that's going on this JVM. So we see that there are 2 garbage collectors. There's one on top and then one on bottom, and we can see that this one is running, this ran once for this JVM, and this ran a couple of times, which makes sense because we're collecting old generation here and just a new generation here. So we can collect new generation often because new objects go there and we discard them often. We also find out what this garbage collector is. And more importantly, if we click here, we can find out all the JVM parameters that we can use to tweak them. At Thermostat, we can't actually modify these at runtime right now, but our eventual plan is you'd be able to modify, tweak, and adjust these all at runtime. Of course, not an email machine, so skip that. Here's another way to look at all the garbage collection that's going on. So the memory tab shows you all the different memory region sizes. So we see Eden, where new allocated objects go. You have your survivor spaces, your old generation. And because I'm running on 8, metaspace. And you can see the typical seesaw pattern here where, garbage collection kicks in, low memory use, we allocate lots of objects, it fills up, and then garbage collection happens, and we go back down. And we can see what the current memory usage is, as well as historical data up here. On the thread local allocation buffer tab, we can see how thread local allocation buffers are being used for this JVM. So we know how many threads are using them, how the sizes of those local allocation buffers are, whether they're too small or too large, are they giving us the right performance benefit? And again, you can select what information you want to display and how long you want to display it for. There's also a heap analyzer, so you can basically see the total size of your memory. So at the bottom here is the total use size, and at the top here is the total allocated size. And again, we see the regular seesaw pattern, memory allocates, and then garbage collection kicks in, allocates again, garbage collection kicks in. We can also do heap dumps and then actually study them in detail. I'm going to come back to this too. On the I/O tab, you can see what the I/O for this JVM looks like. So we not only know how many bytes are being read or written and the historical data, but we also know how many system calls are being used here. On the threads tab, we have a couple of different things. So first, we have a running count of all the threads that are running, and we know how many daemon threads there are as opposed to how many non-daemon threads. There's also the thread timeline, where we can figure out what the state of each individual thread is. Now, if you notice, by default, we're not showing anything here. That's because in Thermostat, our general philosophy is to be very, very low impact by default. So out of the box, we collect a lot of information that we think is safe and won't have an impact on your VM. On the flip side, there's a lot of useful information that may have performance impact. We do not collect it by default. So you'll see buttons around the interface to enable that. In this case, for example, this little play button here. If you hit that, we're going to start collecting information and then displaying that over here. So now we'll see what the threads on this JVM are and their actual state. And you can zoom in and out and look at the history and again, everything. We also have metrics for locking. So if you're interested in how many locks are being used by this JVM, how much contention there is, how many monitors that are being used, how many locks are being acquired quickly versus slowly, that's all here. And this one again is being collected by default. So it doesn't have a huge impact on your JVM, and we always collect this. There's also stack trace profiler. So because we did the thread collection in the timeline, we now have a rough idea of what the performance of this JVM looks like. So we can see the total time was taken up here and how much time was taken in each of the individual call sites. There's the compiler tab, which shows us a lot of the information about the JIT. So we know, for example, sorry, let me back up. So we have two things here. The first one on the top is the current snapshot of the current state. So we know what the JIT has done till this point. We know how many compiles it has done, the total compilation time, the total invalidates, basically a quick overview of what has happened. On down here, you have an idea of what the historical trend is. So what is the total compilation time so far? How many compilations have been invalidated, and how many compilations have been bailed out? And again, you can go back, see how it was in the last second or so. On the classes tab, there is a running tally of the total number of classes that have been loaded into the JVM, their size, how many classes have been unloaded, and their size. So in this case, we haven't unloaded anything, so that's all 0. But if we had, those would show up here. And if you're running some sort of complicated runtime like OSGI, where you're loading classes, unloading them, this is where you'd find out that, have I loaded too many classes, just the right classes? Are they taking up too much code memory? This really new feature that I want to talk about here is Byteman. So I'm not sure how many of you have heard of Byteman. Byteman is a bytecode instrumentation tool. The idea is that you have your JVM that's running your program, and you write a little script that says, here's how to change your running program. And you can change it to do pretty much anything. You can say, do something else when this method is called. Don't call this method. Make a log here, or record this number, or when it's called with this argument, throw an exception. That allows us to do a couple of really, really powerful things. In general, you can trigger conditions that can't normally be triggered. So it's a great unit testing tool, because you can say, when this condition is true, throw this exception. But we care about it because it can be used to dynamically instrument your programs to inject new instrumentation. I'm going to come back to it, but quickly what it looks like is you write a rule, and one of the things, so let me actually walk through the rules. So each rule has a name. There's a class and the method that it touches. There's a helper class that Thermostat provides, so you can actually record metrics. And then you say, when this method is called, do this. And that's just saying send some information. And Thermostat can collect it and really plot it out for you. So let me actually try this out. So I'm going to say Java X swing J component, because I have a swing application. And I'm looking to pass the setVisible method on this swing component class. And when that happens, so whenever setVisible is called, let's send me some data. Let's say demo, Omair, and foobar called. Why not? And then we're going to hit the play button to actually inject this rule into this GUI swing application. So we just injected code into ourselves, and then we're going to collect that and see how that goes. So I'm going to switch over to the metric tab, and something went wrong. Of course. Let's try again. Generate rule template. Oh, let me give it a good name first. Those are the best names. Swing J component setVisible. Oh, I know my mistake. Okay. Test. I didn't call the setVisible method, so let me move stuff around first. So I'm going to switch over to different tabs, switch across to make sure setVisible is called. I'm going to randomly click through things, and hopefully I'll have some data. And yay, so this is all the metrics that Thermostat went ahead into the application and collected it. So we had an application that did not have these metrics. We injected code, and now we have metrics for these. And we can do that for any application that you want. You can also plot this, but I won't have time to go into this too much detail. There's a talk going on that focuses entirely on this tomorrow. I'll post a link to it later. Moving over, we also have JMX notifications. So you can say, show me all the JMX notifications that are happening on this JVM. Again, it's disabled by default because it has a performance impact. Also, we do not want to modify customer JVMs to open JMX ports by default. So not something we do by default. But if we enable it, we should have something showing up. So let me move over to GC for a second, trigger GC manually, come back, and there you go. Now we have the garbage collection, JMX notifications, that Thermostat knows about and can plot. Again, the notes tab, just for taking notes, so hello. And now I'm going to exit this. The other thing I want to show you is the command line. So web storage. So there's two commands, as I mentioned. We're going to start the data collection and everything via this command, and then we're going to use it through another command. So let's run this, and then thermostat. Let's log into the thermostat shell. So please ignore some debugging information. I just built this from master like a couple of days ago. This should go away and release versions soon. But now we have access to pretty much everything that we had on the GUI side. So you can do things like trigger GC, do profiling, do byteman code instrumentation. Everything you can do on the GUI, you can do on the command line too. And if you can't, please file a bug. We really want to keep that feature parity. So again, the GUI shows all the JVMs that we're running. We can see the same information on the command line too. We just did the demo. So I want to spend a couple minutes talking about the components that make up Thermostat. You just saw that we had command line and some data collection and GUI. So let's look into it with a little bit of detail. So Thermostat has these components called agents. These aren't Java agents. These are just Java applications that are running that are responsible for collecting data. So the way they work is that they hook into JVMs via any number of mechanisms. They collect those data and then record it for later analysis and so on. So these fetch from JVMs, from containers, from your host, what have you. And once they have collected that data, they put it all into our central storage. So what that allows us to do is to come back to it later and study it, do any sort of analysis or learning that we want to it. And once we have the data in the storage, we have multiple client implementations. So the sewing GUI that you saw, the command line client, and they all go fetch data from this storage and then process and display it in different ways. There's also a side channel that we have. So what this means is, so the first set of components basically record data in storage forever. This is sort of a side channel that we use to tell our JVMs what to do. So we use this to, say, trigger GC in a JVM or instrument code so we can modify it, not just record data from it. Of course, it'd be pretty bad if our storage was, available to everybody. We want to keep it secure. So we have a tiny security layer in front of our storage. So the storage is actually hidden behind it. And we require authentication and authorization. So you can be sure that only applications that you are explicitly allowing can read data from the storage or write to it. And all the various communications can be locked down as you see fit. By default, when you run local GUI, it's going to keep configuration and security only to enough of it to allow you to use it locally, but not outside. But again, you can all change that. So some of the new features that we've been working on for the last couple of months. So the heap tree map, I didn't show this, but I'm going to come back to it and show that in action in a bit. We saw a bit of the profiling, so we can now profile in a couple of different ways. We have a method profiler, stack trace profiler, and hopefully we are also thinking of doing something with byteman where we can do some more guided and targeted profiling. If you've used Thermostat in the past, you may have been bitten by setup. So before you had to do, create users, run setup, figure out passwords, all that, just to try it out first thing. So now we've done a couple of things. There is a GUI guided setup, so you can actually just create users via that. But also we have like an automatic setup. So when I run Thermostat local, when I ran it just now, it actually created all the users, everything on the first try. So I didn't have to do any configuration beforehand. We recently got tab completion support, so if you're running in the Thermostat shell and you do like list VMs, tab, it will give you all the lists and you type the first 2 letters and you can autocomplete and all that, which is really nice for those who love the shell. We're getting more and more GC information, so we saw a list of all the GC flags that we can use to tune this, and that was recently added. We've also been working on a lot of under the hood security improvements. So we support running Thermostat agent as root, but in a way so that the network communication and the JVM communication is locked down and we don't abuse our privileges. So let's actually try out some applications, see what we can do with Thermostat. This is where the demos get interesting. So first I'm going to fire up Thermostat. Then I'm going to do the demos. So the first demo I'm going to run, well, I'm not going to tell you what it is, but you probably have a good idea that something is broken here. So let's see. We're going to run this for a little bit, see what Thermostat is doing. Okay, it recognizes a new program, and then we're going to kill it. So let's go back. I'm going to ask Thermostat to show dead VMs so I can go back and see historical data. So for this was the broken application. Let's see what we got from it. Overview looks fine. CPU usage was kind of high, but not too bad. Okay, let's skip the profiler for now. Oh, this is interesting. I ran the application for about 10 seconds, 20 seconds, and it did so much garbage collection in not just the new generation down here, but also in the old generation. Well, that's pretty bad because old generation is supposed to contain long-lived objects, not newly allocated objects. So let's see if we can fix that. Should be pretty simple. I think we just need to resize the region sizes. So I have a fixed version. Hopefully you can read this. All right, so the fixed version is pretty simple. We're going to bump our memory region sizes and increase the size of the memory where new objects get allocated in. And the demo gods are not being kind. Okay, I was afraid of this. So a machine apparently has a bug where if you allocate a lot of memory, it goes into swap and encrypted disk, and it likes to hard lock. Okay, let's skip this demo. I'm going to come back to it. So let me restart my machine. And this is all going to be without the demo for now. I'm going to come back to the demos, don't worry. Hopefully the other ones work a little better. So we're going to see Thermostat running in a bit, showing various applications. One thing I want to talk about are plugins. So you saw that Thermostat has various things that you can do. It can gather various metrics. It can record various pieces of information. Let me log in my machine here. Yeah, so it can collect everything that we know about. So we can do memory regions, we can do a processor, we can do all that. But if you have an application, those are really secondary performance characteristics. You don't care about that. You care about things like, is my server serving enough requests? Is it doing what I want it to do? So let's take a hypothetical example. If you have an email server that's just sending out emails, you want to know, is it sending enough emails per minute? And that's the only real metric you care about. Everything else is really secondary. So wouldn't it be great if Thermostat could find out about your application and measure the metric that you care about and not just Thermostat knows about? That would be great, wouldn't it? So Thermostat supports this concept called plugins. And plugins really are first-class citizens, so they can collect, record, analyze really anything. You can make your own plugin to record whatever you want. And it uses the same architecture that Thermostat uses. So every single tab in Thermostat is actually a plugin, and you can write your own plugins. And plugins are loaded in Thermostat using OSGI. So there's a whole concept of we have a defined API. If you use that, it should be safe to use. It should be compatible with future Thermostat versions. Let's go back to the demos. So I'm going to skip demo 1 because that one apparently crashes my machine. Let's try demo 2. Again, I'm not going to tell you what it is. Let's open it up in Thermostat and find out more. So here we see a new program that has appeared, leaks. Wonder what could that be? So let's hop over into the CPU tab. Everything looks pretty okay. Profiler looks okay. Well, GC, not so okay, but it's probably okay for now. Let's see if we can find out more. Okay, so the Eden memory looks okay. There's this sawtooth pattern that we accept. Old looks really, really interesting. We're just allocating memory and it keeps on going up. Let's go over to the heap analyzer. Oh wow, okay, I think we have a memory leak. Let's see if we can find out a bit more about what's going on. I'm going to trigger a heap dump. It's going to take a while because heaps are big, and we're going to download it, store it in Thermostat, and then later use it. So let's see what it knows about. So it knows about this heap dump taken at this time. Let's open it up and see what we find. Okay, so this is a tree map diagram that's showing what's taking up all our memory. And well, there's the very interesting byte array that's taking 300 megabytes. Well, that's interesting. Let's see if the histogram tells us anything. We can sort it by how many, so the histogram really shows us what classes there are, how many instances of those classes, and the total size of those classes. Let's sort it by size. Oh wow, okay, so we have a byte that's taking up all these, but there's more interesting stuff down here. So we have a hash map node that has 34,000 instances. We also have some other data structure that has 34,000 instances. So that gives me a little bit of a hint, right? We're storing it in a map. Okay, it got killed because it ran out of memory. But now we have a fairly good idea. We were storing something in memory in map. Let's see if we can find out what it is. Let me open up this program. And let's read it through. So there's the main method, okay. It makes up a string. makes up a user information. Oh, sorry, it looks it up from a map. That might be it. And if it can't find a user, it does some complicated computation, gets that user information, and then puts it in the map with the wrong key. Okay, well that explains it. The compiler didn't find the problem, but we know that we're abusing a map. Should be straightforward to fix now. The next demo I want to show you is a little more interesting. So this is a sample program where somebody said, hey, let's make a multi-threaded application to do this sort of data collection. And you made your multi-threaded application, but you're getting reports it's really not fast. But we have a multi-threaded application. Why isn't it working? So let's go over to threads and see what's happening. This time I'm going to start the timeline profiling. So you figure out all the threads that are active, and we'll find out what they are doing here. Okay, so these look fairly okay. Alice and Bob. What are these? So let's zoom in. Okay, so there are two threads here running. I hope you can read it. Yeah, Alice and Bob. And they're color-coded. Okay, so blue is runnable and this red is waiting. So if Alice is running, Bob is waiting. And when Bob is running, Alice is waiting. Looks like that multi-threaded application, it really is contending on some shared resource. It's not really multi-threaded at all. And this way, we know, without looking at the source code, without looking anywhere, just what the problem is. We don't care about where it is in the stack. We know that there is a contention problem, and we can fix that now. The next demo I want to show you is of the profiler. So you can probably guess by the name, slow program, what's going on here. So we're going to start profiling this piece of code. So somebody told us that it was not running as fast as it should be. So we're going to instrument it. And now we're going to watch it do its thing. And then we're going to go back to it and try and find out what happened here. That did not work. Let's try that one more time. I wonder if something broke. Let me try that again. Sorry about that. So running Thermostat again. Wonder where that error was. Maybe I shouldn't use the latest version from Head for Demos, something to note. And go back to the demo and see the slow program again. So let's start profiling it again. So we see that we get a little prompt here saying it's starting, and slowly we'll instrument the entire program and record everything. So let's watch the program do its thing again. Okay, well, as I said, the Byteman feature is kind of experimental and it broke something. I'm going to skip this for now. Okay, so the next demo actually I want to show you is for the plugin. So we talked about how plugins can get information that aren't available in other places. So let's do that. I have a separate build of Thermostat here that I'm going to install the plugin in. So let's do that. I'm going to find this custom metrics plugin. I'm going to install that into Thermostat. And I'm going to run Thermostat. I'm also going to run this sample application. Okay, so we have our custom application running, and as I said before, this is an application that's actually sending out email. So then I went ahead and wrote a custom plugin behind the scenes that measures that and shows that information in Thermostat. So if we hop up over, we see our custom program that's here. And if you look in the UI, after everything that was expected, there's a new tab here. So now there's a new plugin here called Emails. And this plugin is showing us the actual emails that are being sent out by this particular program. So through plugins, we can modify Thermostat to record information, store it, analyze it that it couldn't before. And anybody can write plugins to add new features to Thermostat. So just a little bit about the release history. So Thermostat was first announced back in 2012. We did our 1.4 release last year, and we're planning to do a 1.6 release coming up soon. In terms of version and numbering, we have a 2.0 branch where we're doing all our crazy ideas. That's what I was demoing, and there were issues. There's a 1.6 branch where we're putting in stable features and should be perfectly fine. In fact, it should be good to go for commercial use. There's also, for 1.6, we're avoiding any API changes and API breakages. So if you write a plugin for 1.0, it should work just fine on 1.6. And our currently released release is 1.4, where we're just backporting bug fixes from. There's a number of things we're looking at. One major item that you saw was Byteman. We're looking to do further integration there. We're also looking to work on the platform APIs. So right now it's a little bit convoluted to write plugins. We're trying to make it easier to write plugins that fit in, and even make writing the core of Thermostat itself easier. We saw that Thermostat collects data from various sources. It's using a whole number of tools. We're using information from the kernel. We're using information from HSPerf. We're doing bytecode instrumentation. But we want integration with even more tools. We want information from, let's say, Linux's perf tools. We want information from OProfile. We would like to have information from every source gathered, collected, analyzed, and displayed in one place. And of course, we're looking at various further security improvements to make sure that we don't do anything else to the JVMs that we're involved with, as well as making sure it's okay to use Thermostat in a more constrained environment. So right now, for example, we have the agent running inside Docker containers, but we're trying to improve that situation even further. If you want to use Thermostat, it's available for RHEL 6 and 7. Under software collections, and you can just do yum install Thermostat 1 Thermostat. It's also available under Fedora, where you can do yum install Thermostat. If you're not using one of those two, of course, you're not left out. It is an open source project. You can go download our source release, build it, use it yourself. If you're interested in contributing, you can contribute new features or even just ideas, feedback, what have you. If we're interested in collecting even more metrics from different applications, we're interested in porting it to different JVMs and operating systems. As I mentioned, right now we work against OpenJDK on Linux, but it'd be great if we could support everything under the sun. not Oracle. Excuse me. So we're also interested in doing new clients. So we have a command line and GUI client. We're interested in doing some sort of web, mobile, even Eclipse integration, or for any other IDE or tool that you use. It'd be great if we could have all that. We have a mailing list, so feel free to drop by, offer criticism, suggestions, bug, what have you. We have a bug tracker that I forgot to put here, so pardon me. But if you go to our website, ict.classpath.org/thermostat, you're going to find everything. We also have an IRC channel where the developers hang out, where you can ask questions, what have you. So I showed a little bit about the Byteman bit, where we instrument through Byteman, we collect some data, and we display that. There's an entire talk on this tomorrow, given by the author of Byteman, Andrew. So if you're interested in bytecode instrumentation and specifically obtaining metrics through that, be sure not to miss it. And finally, I'd like to thank all of you for listening, and if you have any questions, I'd be happy to take them. Thank you. I'm sorry, you're first, please. Okay, so the question was, do you have to use the thermostat shell? Can you just use thermostat commands from outside in the regular bash shell? And the answer is yes, we do support that. You don't get things like auto-completion. So if you're sitting in bash, you say, give me information about this VM, you won't get completion for that VM name. But if you're outside and you say, oh, thermostat, give me information about this VM, connect to this agent here, you're going to get all that, yes. Yes, please.
Is there any plans to include multiple Byteman scripts or ways to contribute those? Because that would be cool for the UI to say like this.
Yes, so the question was, for those who didn't hear it, are there a predefined set of Byteman scripts that users can use? Yes, there are. Well, we're working on it. So what I just showed right now is like very, very, very early. Like this stuff was integrated. Like the first Byteman bits were integrated like a month ago. So this is all in the works. We have UI prototypes, so we're working on. So the idea is the user would have like a little list of, if you want to instrument JBoss, for example, here's something you might find useful. If you want to instrument swing code, here's something that you might find useful. If you want something computation intensive, here's a script you might find useful. And you would just select that and plug that in and get some metrics out that hopefully are very useful. So the question was, does Thermostat support proprietary JVM implementations? And the real answer is, I don't know. We run, deploy, test against OpenJDK based on the features that we use. So we collect data from HSPerf, from attach agents and various things. Those should be supported in Oracle's proprietary JDK as well. But for IBM's J9, I don't think so, but I haven't verified either way. Yes, please.
Will you show the overview of that again?
All right. I killed it. Okay. So are you asking for the overview for the host, agent, or the JVM?
Yeah.
Okay.
So you have all the tabs, and when you're clicking through them, because you know what you're looking for, something pops out to you. But do you have a way to, like say when you're doing depth analysis, you have the heuristic, the different reports that we run. that are going to bring to your attention the most likely issue. It's a memory or something like that. Do you have in here a way to kind of see in an overview what most likely, is the problem? Because there are aspects of it, like how frequently GC's running full scans. That could be that if this tool is giving you a dashboard in one place, it kind of brings to your attention the most likely thing you're going to want to see, rather than you clicking through all 10 tabs to figure out what's wrong.
Yes, so the question is there one place that gives us an overview of the problems rather than user having to click through everything? And the answer to that is we're working on it. If you see there's a show issues button down there, if you go on that, it's a list of everything Thermostat thinks it has found. It's not feature complete yet. We're still working on this, but right now, let me see if it does stuff. Actually, let me pop over to go here. Let's run that demo again. What could possibly go wrong? Yes, so now we have the demo with what's doing a lot of crazy GC stuff now. And if you go hit that, it figures out, hey, there's a collector that's taking way too long. So yeah, you don't have to poke through everything. We're working on it, so it knows only about a few issues right now. And it's not very intelligent. Those are some hard-coded metrics that we have set that it knows about. And there are different ratings. So right now, it's throwing up a yellow sign. It's not a red saying, oh, this is definitely broken. So, yes, please.
Yeah, sorry, just to add to that. So I run a company called Clarity where we do some analysis on all of these type of metrics. So we're really chatting to about bringing some of our analytics to this platform. So we're hoping we can help bring that area out as we know. So we're definitely reaching out into those platforms and stuff like that. Yeah, I'm hoping that over the next year that we'll be able to come up with ourselves.
Well, I guess this is it. Thank you, everyone, for joining me. Hopefully, you learned something very useful. And please feel free to send back feedback, bugs, comments, suggestions, criticism, anything to our mailing list or IRC channel. I'll wear my flameproof suit. Thank you very much for joining me.